Thank you, Leon, for the introduction, and thanks everybody for having me here. So today I'm going to talk about the project that we've been working on reducing agricultural runoff. Um, so um, so sprays are ubiquitous in agriculture. There are people like these who are spraying pesticides and so on, and you can see that most of these people don't wear any protective equipment. If you look at large scale farms, there are sprays like these. And even drones today are used for spraying. So you can see that a large quantities of chemicals are sprayed in farming, and in a way this is essential to keep sort of the bugs out and to protect the produce that's being produced, or other grains or other farm products that are being produced. So, but however, there are significant problems with these sprays. Firstly, there's a lot of runoff because these pesticides or other kinds of chemicals that are sprayed, they can basically pollute the soil and groundwater because they run off from these plants and fall into the ground. They can then get into our groundwater. They can also, there is significant amount of drift, and therefore these pesticides can have long distance as well as short distance transport. And for individuals who are spraying like these, these can basically, without proper protective equipment, they are ingesting these chemicals. So this has led to a significant amount of deaths and other issues, including cancer and so on. However, the market for pesticides is significant. It's about $60 billion and growing globally. And again, these are needed to be able to protect the plants from pests and other things. But the other important thing is that a major part of the production cost. Um, but so the question is, like, why do we have to spray so much of pesticides? So if you look at, most plants are, hydrophobic or even super hydrophobic, which means they're highly non-wetting. So whatever sprays are being used, the retention is actually very low. So as a result, actually, these sprays then hit the plants and actually kind of fall off, and that leads to significant runoff. And to potentially improve this retention, people use chemicals like surfactants. These are called adjuvants, and that actually leads to even further issues such as making much finer droplets that are prone to drift. So believe it or not, only like 2 to 5% of what is sprayed is retained by on the target. So actually, a significant amount of spray is being done, of which most of it is becoming pollution. Um, and so what we are trying to do in this work is to fundamentally solve this problem. um, and so we went back to the drawing board and looked at this from a basic physics point of view, and we see that there's an important time scale here, which is as the drops impinge on surfaces like these and before they bounce or splash, there is a contact time. And so the question is, whatever interaction that needs to happen between the drop and the plant surface has to happen within these time scales, which are 10 in tens of milliseconds. So in terms of prior work, people have, as I said, used surfactants there to improve, to actually reduce the surface tension. But because these surfactants take hundreds of milliseconds to actually get to the interface, they have been rather ineffective in sort of improving this retention. But then they also exacerbate the drift problem because they can lead to much smaller droplets. There's other work on using viscosity modifiers, and these tend to actually, while they can actually improve the stiction, it's harder to spray, and other issues such as phytotoxicity are still yet to be determined. So our approach actually plays on using charge interactions, and by using charge interactions, we are able to do this in the short time scales that we talked about. And so here what we do is we spray oppositely charged droplets, and when they come into contact, they basically, these materials and precipitate and arrest the droplets on the leaf. So here are a few examples. So this is a regular spray. And on the regular spray, what you can see is that the droplets are impinging and are bouncing off of the surface, and this is kind of what causes the uh, uh, lack of retention. And now when we have our oppositely charged droplets, what you see is as soon as they sort of come into contact with each other, as you can see, these basically lead to local precipitation and pinning of the contact line. And that can then cause these drops to be arrested on the surface. And so very quickly, these videos are high-speed videos, so happening in a few milliseconds, we are able to now get complete coverage using this technology that we have come up with. And what we have seen in the lab is about 10x improvement in retention. So what we find is essentially, for the 100% coverage, we are able to use, at least from the lab scale, 10-fold reduction in pesticide use by using our approach. And because our approach doesn't depend on the drop size, we also have a potential to reduce drift. So what we have done since is we've actually gone forward and actually used this for taken this to farms and worked with a number of farmers. And here, these are orange groves in Florida, working with a King Ranch farm, and we are able to show that we can get very nice coverage. And so quickly, to give you an economics of what kind of savings this can do, you're looking at, so let's say, take example of cotton in US. Its acreage is about 10 million and pesticide spend about $100 per acre per year. So you're looking at the total pesticide spend just for cotton, about $1 billion a year. So if we are able to even save, forget about the tenfold that I was talking about, even if you do 50%, you're looking at and if we were to like commercialize this, which we are, by the way, at the moment kind of trying to do, and you can hear about this, one of my team, our team is kind of presenting this at the 100K competition. But if you're able to do this, you can see that, even if you get 30% of those savings, this leads to about a $150 million a year revenue opportunity. And so if you extend this to global pesticide market, again, sort of rough calculations, but the TAM here is about 9 billion. And so so there's significant value on the table that can then be, by commercializing this, we can make those savings possible. So we have also taken this and looked at, in California, where we have almonds and pistachios. Again, retention here is poor. We worked across, internationally as well. These are vineyards in Italy. And we can see, with our formulations, we are able to get very nice coverage. And we also built this spray system where we can do the simultaneous positive and negative sprays. We also tested this locally here, working with a local farm. We were able to do a lot more systematic experiments over the last couple of years. This is Wardsbury Farm in Massachusetts. We actually built a custom sprayer and were able to hook it up to their tractor, basically retrofit this onto their tractor. And we've done both greenhouse and outdoor spraying. And and sort of this system allows us to then do the kind of sprays that we are talking about. And indeed, we were able to take this and demonstrate this in this farm in Massachusetts. And we got a lot of had great help and great collaboration with the farm. Jim Ward, who is the owner of the farm, has been extremely kind and helpful in letting us use his property to do our testing. And we found some great results here. What we found, these are some examples with kale. Just as is, you can see that hardly any retention of the sprays, and we are seeing almost 60% reduction and actually increased spraying speeds, which is very valuable for the farmers because that reduces the operational time, and they can cover more acreage. So this work was also kind of featured on the BBC. There's a Follow the Food program that was done by BBC, and we are grateful for their help and support to get the word out. And finally, what are our next steps? We are trying to now take this. So we spent a lot of time developing the technology and doing field testing. We feel comfortable with the kind of savings, and so we are hoping to take this forward and commercialize in the next couple of years. So once again, I want to thank the MIT Deshpande Center for all the help, the JWOFS program, and the Tata Center who initially funded this work, and the JWOFs who helped us in this translation, and the Deshpande Center as usual for the amazing support on the entrepreneurial as well as scale up and taking this out to market. So once again, I want to thank everybody's help in this process, and I'm hoping that this technology, which can be significantly can bring a lot of savings to farmers, but also tackle an important environmental problem. I'd love to see this commercialized and taken to market. Thank you very much.